Okay guys, welcome to the next set of notes. We are in Unit 4, Topic 2 now, Charges of Cations. And you might be saying, well, we already talked about cations back in 4.1, but the thing is, there are special ones. So the transition metals, we didn't cover, if you might have noticed. And the p block also sometimes act funny. So the reason these act funny is they have some d block electrons that are going to do some weird things. So that's what we're going to look at today. Before we go any further, let's just refresh what is a cation. So a cation is a positive ion. It's going to be made from a metal. So metal atoms lose electrons, so they lose electrons. And when they lose electrons, or an electron or electrons, they become positive. Remember, if you have an atom, it has an overall no charge. And if you lose an electron, if you take away an electron, you're subtracting a -1 charge. So that's going to give you a +1. So when you remove negativeness, you become positive, right? So removing electrons becomes positive. You can also think of losing becomes positive. So these are just a few things to remember about our cations, what they are. Now let's do some bookkeeping of what we learned last time. So we are going to draw out a very basic periodic table. We are not going to draw the whole thing, do not worry. All right, so I'm drawing the S block over here, and then here's our D block. I'm not going to draw the lines within the D block, don't worry about that. And we're going to bring this up. This side goes over a bit further, but we're not going to label the P block over here because the P block is mostly nonmetals, and we're not too worried about that. So we're worried about the metal side, which remember is here over, okay? So in here, we're going to ignore hydrogen. So hydrogen's here, we're going to pretend that's not there. We're not going to talk about hydrogen. Helium's over here, we're not going to talk about helium at all, so we're pretending those don't exist. Remember that everything in this group right here, these are the alkaline metals, these all have one valence electron. So when they form cations, they're going to lose that one valence electron, and all of these have a 1+ charge when they become ions. So everything in this group, remember we're ignoring hydrogen, these all make a 1+ charge. So whether it's an atom of rubidium, an atom of lithium, any of these in here are going to be those 1+ charges. If we go to here, the alkaline earth metals, these all have 2 valence electrons. So those 2 are going to be lost when they become cations. So these all have a 2+ charge. So whether it's magnesium or calcium, it's going to be a 2+ charge all the time. The transition metals make different charges depending on what element it is and what the conditions are. There are a few, however, who always make the same charge. So we're going to go over those. So the first one is zinc. Whenever zinc makes an ion, it always makes a 2+. So you want to write that down so you know if you see a zinc ion, you know it's 2+. Under it, cadmium always makes 2+ as well. Next to cadmium is silver. Silver always makes +1 or 1, or just the plus sign. The only other one that's memorizable is aluminum. Aluminum goes with the valence electron trend. Aluminum has 3 valence electrons, and it makes a 3+. Besides that, the rest of your metals, so remember your metals kind of make a little ch-ch-ch-ch. So these and all of these all can make multiple charges. And you have to either read the formula, like read the name, and I'll show you how to get it from the name, or you have to do some detective work to figure out what's going on. So let's do an example of what charges a very common metal that's in the transition block would make. So let's talk about iron. Oops, spelled that wrong. I-R-O-N. So iron is a transition metal, right? It's over here. And iron has 26 total electrons. So if we look at the electron configuration of iron, it's going to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6. So let's look at a periodic table so you can see where that is. So that's right here. So here's iron. Remember, we have to go through everything to get to iron, and it ends 4 minus 1, so 3d, 1, 2, 3, 4, 5, 6. So you have to start with 1s2 always. We're ending with 3d6. So when this makes an ion, it will lose its valence electrons first. Every time you're making a cation, so making a cation, you always lose valence electrons first. So if I look at my big numbers here, I've got 1, 2, 2, 3, 3, 4, 3. So here are my valence electrons. So we can see that iron has 2 valence electrons. So when this is going to make a cation, these are going to go. If I lose my valence electrons, there are 2 of them, iron has lost 2 electrons, so we can make a 2+ ion. This is going to be 1s2, 2s2, 2p6, 3s2, 3p6, 3d6. So we haven't done anything new here. This is what we learned last time. When we're making cations, we're always losing valence electrons, and you're losing all the ones you have. This one only has 2. But if you look at this, this is a little different from before. The reason is, if I look at this, those up to 3p6, that's argon, right? And then we still have 3d6. So we have not made something that is actually electrically like a noble gas anymore. So this is called a pseudo-noble gas electron configuration. This is something that's unique to our D block metals and our P block over here because we have those D block electrons to deal with when forming our cations. But the thing is iron can also make an Fe3+ charge. So when iron makes a 3+ charge, it's lost 3 electrons. It's always going to lose its valence electrons first, and then if there's more to lose, it comes from highest D block or P block, depending on where it is. So like if it's one of these, they might lose a P block electron. That would be a valence electron anyways, but you always think of valence electrons as the S really for metals. But remember, these have P block valence electrons as well. All right, so iron 3+ has lost these 2, but it has to lose 1 more. So this is going to lose 1 from here. So this one's going to be 1s2, 2s2, 2p6, 3s2, 3p6. We don't have the 4s2. We lost 2 there. And then the 3d6, we lost 1 to make 2 + 1 is 3. So this will be 3d5. If I were to write this in noble gas electron configuration, remember this is argon for these electrons, and then it has 3d5. So again, this is a pseudo-noble gas electron configuration. Now, when you're reading names of substances, the way you can tell what the charge is, since it's not always a set charge, is it's going to list the name of metal, and then in parentheses, it's going to be the charge of metal in Roman numerals. And then I'll continue with the name. So for example, iron 2 oxide, this is made of Fe with 2+ charges, versus iron 3 oxide, this is Fe 3+. The Roman numeral always tells you the charge of that metal. The formula, by the way, for this one, this is going to be FeO for here, and then this would be Fe2O3. And we'll get to the naming and the total formulas later in the unit, but you can see it does end up making a totally different substance. They have different properties and everything. In case you haven't seen Roman numerals before, they are, so you can put the lines on top. I'm generally lazy and I don't write them in the names, but you can. So that's 1, this is 2, 3. So each of these single bars means 1, but when you get to 4, it's saying 1 before 5. So V is 5, so 1 before it is 4. V is 5. V1 is 5, but 1 after it. So this is 6. 7. 8. And then 9 is 1 before 10. 10 is an X. X is 10. I've never seen anything with a positive 10 charge, but could be. Whenever you see these with naming, this is always a positive charge. Okay. You only do these for the ones that have multiple charges. So if it's anything in the alkali earth, alkaline earth, or one of these 4, they're not going to have a Roman numeral. Everything else gets a Roman numeral. So for example, you might have scandium 3, right? So you know, and then let's maybe say this is chloride. You know that scandium is making a positive 3 charge, and your chlorides are always making -1 because that's what chlorides always do. You might have something like titanium 4 oxide, right? So this is saying that you're making a bunch of titanium 4+ ions, right? This 3 is saying that it's Sc3+ ions in it. It doesn't mean there are 3 scandiums. In fact, the formula for this is ScCl3. Notice there is only 1 scandium within this. So this is talking about, this 3 is talking about charge, not how many. Titanium 4 oxide, the formula for that is TiO2. Notice there isn't even a 4 in this chemical equation. So this specifically talks about charge. All right, and we will go over how to make the names, in the next set of notes, but for now, you need to be able to do an electron configuration and figure out which things go first. So first, you lose valence electrons, and then second, lose d block electrons. And that's how you're going to make your cations. The total things you lose, so however many valence electrons and d block electrons, that's whatever your charge is. So if you have a charge of +5, if that's your charge, so you have some element and made a +5, this means that that atom lost 5 electrons. Chances are it lost 2 valence electrons and 3 d block electrons. It could have lost some p block electrons as well, though, so you just have to do some investigating. It depends on your atom, whatever makes the most sense. So remember, your valence electrons are s and p block. They are the highest numbers. Most of them just have s, but if they're in the p block, then they'll have a few p block electrons as well. If that's not enough, then go to the d block, but you're always going to lose those outer energy level electrons first. So if your atom looks like this with electrons, so you've got 1, 2, 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. If this is who you have, so this is zinc. So overall we had 10 in here, 18 in here, 2 in here. So this would be what zinc would look like. Zinc always is going to lose its valence electrons, these outer electrons, before anything that's tucked in. That's why valence electrons go first. Now zinc always makes a 2+ ion. The reason is all of its inner shells are completely filled, so they're very stable. So zinc never loses any of its d block electrons because in zinc, all subshells are filled. So losing 4s2 is still stable. All right, so if we have zinc 2+, we're going to have 1s2, 2s2, 2p6, 3s2, 3p6. We no longer have the 4s2, those two left, but then it has 3d10. Everything here is filled, which means it's very stable. You're not going to be able to remove one of these electrons from 3D because it's filled, it's done, you can't touch it. So that is how you figure out what charges and how the electron configuration is related to charges of cations. Okay, let me know if you have any questions. Otherwise, I will see you in the next set of notes, guys.